So back to the proof of the maximum value theorem. Which, as we all recall, says that if S is compact and f is a continuous real valued function on S, and we did discuss in class yesterday what it means to talk about continuous function on a set that is not all an open set on Rn, but it just is an arbitrary subset. We discussed that. Then the statement is that f takes on its minimum and maximum values in particular. This means we have points in our set. So whatever our set looks like, we have points in there where the function is respectively the smallest and the largest. So that f of y is less than or equal to f of x is less than or equal to f of z for all x. And not surprisingly then, this is the minimum value. This is the maximum value. Now the proof is going to rely on one very important tool, and although I'm holding everyone responsible for the proof of this theorem per se, the tool proof, which we'll do in a few minutes, is not going to be part of what you're responsible for, other than to understand it and be able to use it. So the important tool, which might be referred to as a highly useful proposition, states that if you have a sequence of points in a compact set, you might ask whether that sequence has to converge just because the set is compact. So because the set's compact, your sequence can't go meandering off to infinity, but it isn't hard to see that you could have something like a sequence that bounces back and forth, never going very far except it keeps bouncing. It's obviously never going to converge. So the best you can hope for then is that it will have a subsequence that converges. So in this example, you could just take the alternate terms, namely the ones that just sit here, and that would give you a sequence that converges to that point. Or you could take the ones that are sitting here. Or you could take a certain number that bounce back and forth, but eventually settle down and keep staying in one of the points. Now, I'm going to talk about the notation for subsequences in a second, but we're going to put a double index because we're going to choose certain elements from our sequence. And I want to comment that the limit of that subsequence must necessarily be a point of S because S is closed. So if you have a convergent sequence of points in S, the thing to which it converges must be in S. So let's just talk about this notation for a second. So you're starting off with a sequence which we're calling the xk's. So that means here k is going to be a sequence of positive integers, and you're having various points in Rn, one for each counting number, one for each natural number. Now what you're going to do when you make a subsequence is you're going to come along and you're going to choose certain ones of these natural numbers that you're going to work with and not use the other ones. So a subsequence is given by choosing what we're going to write as the first k you want to pick, and then the second k you want to pick, and then the third k, and so forth. And the prescription here is that you have to proceed in order as the subscript increases. In other words, you can't go from x2 to x5 and then come back to x3. You can't do that. You have to keep moving to the right in the list of integers. So this could be your first one, this could be your second one, maybe down here this would be your third one. Maybe that's your fourth one, and so forth. So you're just choosing positive integers that keep getting bigger. Again, though, one for each counting number, one for each natural number. And that is a subsequence. So then, using the particular integers you've chosen, this is your subsequence. Now it's worth commenting that, we'll use this later, note that as j gets bigger and goes off to infinity, because the integers keep getting bigger and bigger and bigger, of course, the terms you've chosen in the original sequence, those subscripts have to go up to infinity. And in fact, indeed, what's the smallest number that kj could possibly be? Well, the smallest number you could possibly get is if you just took and never jumped. So if you just went 1, 2, 3, 4, 5 and took the whole original sequence, you would get the most conservative choice of integers that marches off to infinity as slowly as possible. So at any stage, the jth one in your subsequence, the index has to be certainly j or bigger. So as j goes to infinity, of course the kj's are bigger than something that's going to infinity, so they go off to infinity. Okay. So once again, just to emphasize, the compact set here is giving me guaranteed anytime I have any sequence of points, there is some convergent subsequence. So let's now use this highly useful proposition to prove the theorem. So just to remind everybody that you shouldn't forget about this forever. Okay. So first step is going to be to consider the values of the function f. Consider the set of values of f as x varies over the set S. And I'm going to draw you a picture sort of the values on a vertical real axis here. So here you are moving around your set S, and you think about what values your function takes as you move around. The function values vary around the various places. And the question is, could this set of values of f manage somehow to get off to infinity? answer is no. The claim is that there is a capital M so that all y in y satisfy their absolute values bounded by M. So what I'm saying here is there is a capital M so that, i.e. satisfy, i.e. so that f of x is between capital M and negative capital M for all x. So that's going to, once we know that the function's values are bounded, then we're going to be able to get our hands on what the maximum value has to be. So let's first off just try to deal with one side here, and you can think a minute about how to get the other side when we're done. And like most proofs where you say there is some M and you're really not sure exactly what it is, most proofs like that are going to proceed by contradiction. So suppose that there were no such M. Suppose you could find no capital M so that the values are all beneath it. Well, then that would have to mean that any M you picked, there's some place where the function's bigger than that. So if there is no such M, this means that for every positive integer k, there is some point x sub k in S with the value of the function at xk bigger than or equal to k. So for every k, you would find, for example, there a value of the function that occurs at some point that's at k or bigger. And because there's no upper bound, we're hypothesizing, this means as I move k up, I can always find some f of x sub k that's bigger than whatever k I'm at. Well, this is bad news, because this means I now have a sequence of points in my set S. Who knows where they are, but I have a sequence of points with the property that the function values are getting bigger and bigger and bigger. So i.e. we have defined a sequence of points in S. Well, so by the highly useful proposition, what do we have? We don't know that sequence converges, but we do know that if we pick out certain ones of them, that subsequence is going to converge to somebody. So there is a subsequence, x sub k sub j, that converges to some point, which we said is actually a point of S. Now I haven't, to this point, used one of the main hypotheses, namely that f is continuous. You see a sequence of points converging to a point, so because f is continuous, we know that the sequence of values of f at this sequence, subsequence is still a sequence, must converge to the value at the limit point of that sequence. Well, that's bad news. What are these numbers doing? Well, f of x sub k sub j is at least k sub j, which we said, remember, is at least j, if you want to remember that. So what's happening as j gets bigger and bigger and bigger? This is going off to infinity. That means these guys are going off to infinity. And yet, they're converging to f of a, which is 12. Not too good. I think that's a contradiction to something. So you can't have a convergent sequence converging to some real number and yet have them diverging to infinity. So this is a contradiction, which means what? Well, we said we got in this position by supposing no such m exists. That got us in trouble. So in fact, some m does exist. So some m does exist. So that took care of showing that there was some upper bound for the f values. You could start all over and repeat the argument and switch it to why there's a bound on the lower end. You could say, well, if there weren't on the bottom end, then for every positive integer, there's some point where the function is less than or equal to minus k, and you could go through the exact same argument. But a lazier way to complete this is just to say we've proved for any continuous function that is defined on a compact set that has an upper bound on its values. So just apply what we've done to minus f. So we know that negative f is bounded above. And if you sit down and write down the algebra, you'll see easily that that says that f itself is bounded below. Okay, so that's step one. What's step two? So step two now is to actually show that we have a maximum value. So we know the function values are bounded above. We want to now argue that there is, in fact, a maximum point. I remind you of pictures like this that you saw in single variable calculus, where in fact you have an upper bound on the values of the function, but because you have a horizontal asymptote, you never take on that upper bound value. And if you lower it down to the point where you're taking on the value, well, oops, it's no longer the maximum value. So we're going to use some stuff from chapter 2 by the least upper bound axiom for the real numbers. We have our set Y of values of S. It's a non-empty set of real numbers that's bounded above. Then it has a least upper bound, or lub, which we called the soup, and let's call it beta. So remember, what you can think about here is you have at least one upper bound for the set of y's, wherever they are. And you can imagine a little beam here on this stalk, and you can imagine gravity pulling it down until it can't pull it down any further because the set stops it. that's going to be where the least upper bound occurs. So you move the upper bound down until you can move it down no further without crossing into y. And let me point out, let me remind you that a consequence of the definition of the least upper bound is that if you specify any distance, no matter how small, that you want to move below beta, there have to be elements of the set in that interval there. There have to be elements of the set y within this prescribed distance of the number beta. Because if there were no such y, gravity would have tugged beta down lower. So the precise statement of that is, the consequence of the definition is that given any delta bigger than 0, which is this distance here, there must be some x with f of x between beta and beta minus delta. So you specify a distance delta, and I guarantee you that I can find function values that are between, less than that distance away from beta, between beta minus delta and beta. So we're going to apply that and just create another sequence. So how can I get a sequence of points in x and s? Well, I want to think of a sequence of these deltas that shrinks down to 0. So I want to force these function values, these blue function values here, I want to force them to get closer and closer to beta. So apply this with delta equal to 1 over k. So you specify with delta equal to 1, you specify that you want a point within distance 1, and I say, sure, there has to be such a point. And then you shrink, and you say delta equals 1/2. Well, there has to be a point in there. And you keep shrinking delta, and as you do, these blue dots approach closer and closer to beta. So for each natural number k, there is a point in S, yet again, with the distance between beta and that point x of k less than 1 over k. Or less than or equal, doesn't matter. So I'm rewriting this slightly differently, but I'm saying the distance between beta and f of x is less than or equal to the distance between beta and this point, which is delta. There's my delta. So what have I got? I've got a sequence of points in S. So by the highly useful proposition, yet again, there is a convergent subsequence . So there's some subsequence that converges, and I'm going to call the point, for some mysterious reason, z. Well, it almost fits on the board, not quite. Well, what's the end of the argument? Again, by continuity, what happens when I take f of these? It converges to f of z. Well, I don't know what f of z is. But what do I know about these guys? I know that f of x kj is between beta and beta minus 1 over k sub j. So what happens as j goes to infinity? Well, this sits there. These approach beta. As j goes to infinity, k sub j goes to infinity, the reciprocal goes to 0. So this is approaching beta, this is a beta, so it follows that the limit of the value of the functions at this sequence of points is in fact beta. So that means f of z is beta, and that is the maximum value of the function taken on at the point z. Beta is the maximum value. Okay, again, now, if you want the minimum, I've erased the statement of the theorem, but if you want the minimum as well, you could start all over again and do everything instead of with soups, with infs, and argue the exact same argument, carbon copy, that you get a sequence of points, take a convergent subsequence, the values go to the inf. But I'm, again, going to advocate laziness. Again, apply the same proof to minus f. It has a maximum. This argument applied to minus f produces a point y, which is a maximum point for the function minus f. And this means that y is the minimum value of f of x for all x. Yes. So that's the proof. Okay. Very conveniently now we have our highly useful proposition. To talk about most of the proof of why that works. I'm going to start with a special case. Suppose S is just a closed interval in the real numbers. I want to try to see why there's a convergent subsequence if all the points are in the closed interval. Intuitively, except in one situation, you want to think about how, if you have an infinite set of points in this finite closed interval, it has to accumulate somewhere. What we want to do is find where it must accumulate. Now, you could object that your sequence of points might do something like this. Somehow this sequence isn't very creative, and it gets locked into just having a finite number of values. So what if the set of values of this sequence of points, as k varies, is just a finite set? So there's only 3 values here that the various xk's are free to choose among. Then I don't see them really accumulating, but you do want to argue that at least one of these 3 values must be taken infinitely many times. Well, again, if not, you would have a finite number of k's that land you there, a finite number of k's that land you there, and a finite number of k's that land you there, thereby accounting only for a finite number of k's. But we have infinitely many k's, so it has to be that at least one of these piles has infinitely many contributions to it. So choose a subsequence that hits the same value infinitely many times. So choose a subsequence consisting of the xk's infinitely many of them landing on a single value. So the interesting case is that in fact you have infinitely many distinct values so this is the standard computer science application now here. Is used in all sorts of different settings. Binary searches among them, trying to find a root of a function numerically. So the idea is very simple. You say, okay, I have infinitely many dots in this interval. Split the interval in half. Well, they have to be infinitely many in one of those two halves, or else, by the same argument I made down here, you'd have finitely many in this half, finitely many in this half, doesn't make infinitely many. So at least one of the two halves has infinitely many points in it. You could say split the interval in half and choose the half with infinitely many points. Now you may complain, I hear you complaining right now, that there might be infinitely many in both halves. Fine, pick the left one. So the rule is going to be, if both halves have infinitely many, choose the left one. That's now my next interval. And I'm going to repeat this process ad infinitum. Take the first interval, I1 now, split it in half. Well, there have to be infinitely many in that half, or infinitely many in that, or both. If both, go to the left. Otherwise, pick the interval that has infinitely many in it. Divide it in half. Running out of colors. Etc. So you keep successively dividing in half, and what you notice is that the length, once you divide it into k pieces, is the original length divided by 2 to the k. I divide it the first time, it's half. Each time I divide, it's another half. And what do you notice about these lengths? Well, you notice that these numbers are going to 0. So these intervals, as I keep chopping, must be converging on some point in the original interval. How can I actually get that point? Well, take alpha by following the left endpoints of these intervals. Here you are at the left endpoint of I1, left endpoint of I2, left endpoint of I3, left endpoint of I4. Notice that these actually keep getting bigger. And so you can take the soup of the set of left endpoints of the various intervals. We have a non-empty set of numbers that's bounded above, certainly by B. So there's a soup. And that actually is going to be a point that these intervals are converging onto. How do I create my subsequence? how do I choose a subsequence of my original sequence, no vectors. How do I create a subsequence of my original sequence of xk's that's going to converge to this point alpha? Simple. Just choose any point x, k, j in the jth interval. Each of these intervals has somebody, it has infinitely many of my original sequence in it. Pick one of them. And so in the jth interval, pick your jth element of your subsequence. And now, because these subintervals are shrinking down, approaching this point alpha, these points, this subsequence is going to get dragged to that point alpha. So that's the main idea. Okay, now we just have to jazz it up slightly. Move on to n equals 2. So that was the first case. Second special case. Suppose S is a closed rectangle in R2. So it looks like an interval in the first axis, an interval in the second axis. You've got yourself a rectangle. And you've got a sequence of points in your closed rectangle. So you could try to just repeat this argument by dividing the rectangle into fourths, and then picking a fourth, and dividing the fourth into fourths, and picking successive fourths. And you could imagine trying to do that in n dimensions. But I think it's a simpler idea to try to reduce to the case we already did. Now you have to be a little sneaky here, because if you try sort of the most obvious thing, you get in trouble. Not having a pigeon to try the obvious thing here, you could try to say, well, here's a sequence of real numbers in the closed interval. It has a convergent subsequence. Take it. Here's a sequence of numbers in this interval. It has a convergent subsequence. Take it. What could go wrong? Well, maybe the k's that gave you a convergent subsequence for these guys were the even k's, and the k's that gave you a convergent subsequence for these guys were the odd k's. How do I put them together? I can't. So you have to have the brilliant idea to consider the sequence of x's and take a subsequence of it, ignoring the y's. So look at the x coordinates, the first coordinates of your vectors, and choose a subsequence which converges to some point, let's say alpha 1. Go back to those original vectors in the closed rectangle that gave you that subsequence. They may not be converging up here, even though the x-coordinates converged. But now comes this trick. Look at those y's as a sequence in this closed interval here. So correspondingly, the sequence of y's for that subsequence, but think of that as a sequence now of y's in this closed interval here. Well, it has a convergent subsequence by what we already proved. So now, when you take a subsequence of this subsequence, this is where you start to groan, because you run out of letters. You have cascading subscripts now. You have, as L varies, you have a subset of these k sub j's that you're picking. And that's converging to some point alpha sub 2. Well, it shouldn't take you too much thinking to convince yourself that if I now take that subsequence of my original vectors, that that's going to converge to the point whose coordinates are alpha 1 and alpha 2. Certainly you know that the second coordinates are fine, but what about the first coordinates? What about the first coordinates? I'm not taking my original convergent subsequence, I'm taking a subsequence of my original convergent subsequence. Well, fact, any subsequence of a convergent sequence converges to the original limit. So by starting with a convergent subsequence for this guy and then successively taking more subsequences, I'm creating a subsequence that converges in every coordinate. You could do that, in fact, over and over and over again, n times, and you would have a proof for a closed rectangle in Rn. So repeating this a few more times proves the result for a closed rectangle in Rn. Better yet, do an induction proof. You can see the book for that. So the idea is, think of this picture as representing Rn, and think of this as being Rn minus 1. And this is just being your extra dimension there. You take your sequence in your closed box in Rn, you project it into Rn minus 1. You assume that you already know how to handle it, and that you've proved the result in dimension n minus 1, so you have a convergent subsequence of these. That's now playing the role of these guys. And then you play the exact same trick. You look at the corresponding coordinates in the nth direction, that's these guys, and you do the exact argument we just did here. So you can see that written out in the book. Okay, last step. You might complain that all I've done here is closed rectangles. Well, I don't care. I like rectangles. You have this general compact set. What do you know about a compact set? It's bounded. So your general compact set is in some ball centered somewhere. That ball, in turn, is contained in a rectangle. So, by what we've proved, if you have a sequence of points living in S, you can think of them instead as living in a closed rectangle that contains S. So this sequence of points that was in S is in fact sitting in this big rectangle R. By what we've proved, you get a convergent subsequence converging to some point in R. So from what we've done from the earlier case, we know there's a convergent subsequence that converges to a point of R. Okay, so here you are, you have your subsequence, and it converges to a point out here in R. Is that reasonable? Someone says no, it's not reasonable. Why must A, in fact, belong to S?
Because it's closed.
Because there's this other hypothesis about compact sets. They're closed and they're bounded. So we used bounded here. Now we're saying, because you have a sequence of points in S converging to a point, and S is closed. So that limit of that convergent sequence must be in S. And that proves the end of the highly useful proposition.